Okay, hello everybody. So we start the fourth day of the LMS Summer School, and today we have the third lecture of Sophie Morier-Genoud. And as you know, the title of the course is, of course, Arithmetic and Combinatorics of Conway-Coxeter frieze patterns. So please, Sophie.
Yes, so thank you. So we actually have two lectures today. So the plan was to first try to outline the proof of the main theorem. What I call the main theorem is this one-to-one correspondence between frieze patterns and triangulations of polygons. And then I want to go back to the notion of continued fractions and explore the more links between the objects. And in the next lecture, it will come just after this one, I want also to go back to the Hirzebruch formula and also try to outline how to prove it. And this then will be more discussion. I want to just mention some, we focused on combinatorics and arithmetic, but there is also actually a lot of geometry behind frieze patterns. So I just want to discuss some of the geometry, which were actually the motivation for the frieze, and then also talk about some new developments in this area. So I think all the parts here will be independent. So if you are kind of lost at some point, probably not, but you will be able to follow the next part. Okay, so I recall here this main theorem, which was this correspondence between frieze with positive integer entries and the triangulations of polygons. So we had the recipe, we saw the recipe to construct this bijection is given a frieze. So we already know that frieze are periodic. So you just look at the first row, you just take a cycle on the first row. And this you should be able to find a triangulated polygon so that these numbers count the triangles at each vertices. Okay, and conversely, if you start with a triangulated polygons, you want to understand that taking this number and put them in the first row of a frieze, you are able to compute a frieze with positive integers only. Okay, and remember, for a triangulated polygon, this sequence will be called the quiddity sequence. So I use this terminology. So of course, the proof will be in two steps. So we want to show that the first frieze, the first row of a frieze is a quiddity sequence. And we need to do in the other direction, we need to show that a quiddity sequence defines the first row of a frieze. Okay, so okay, and now for the proof, I can work up to circular permutation. Okay, this is periodic, so I will choose a cycle and show that this is a quiddity sequence. And sometimes I will just maybe choose a particular cycle just to make thing easier. So anyway, so the first, of course, it's not, I mean, that's how we will proceed. We will proceed by induction. So that's the main ID, but it's easy to have this ID when you have finite set. What is so the induction will be on the period or on the width of the frieze. So remember that the period of a frieze is the same as the width plus 3. And so usually I will use the letter N for the period and the letter W for the period. That means if here I would prefer to use the letter N. Okay. And that's the induction will be on N or on W if you wish, they are related. So last time we did the first step for the induction. If I go back to the slide that was here, it was from the previous section lecture. We checked for W equals 1, meaning for period 4, and so meaning for squares. And we also checked, I mean, we did not really check, but it was an exercise. So the first step of the induction is okay from here. And now we need an induction step. So we need to understand how to go from some n to n plus 1, or to go from n plus 1 to n. And the idea is quite simple when you look at a triangulation. So let's draw a triangulation. I don't know, 1, 2, 3, 4, 5, 7, for instance, and draw any kind of triangulation here. Okay. So if I have an n-gon, and if I want to consider a triangulation of a n plus 1 gon, there is something very easy that I can do, is I can just glue a triangle. If I glue a triangle anywhere, for example here, if I glue a triangle, I will have a triangulated n plus 1 gon. If I start with an n gon, I glue a triangle, I have a triangulated n plus 1 gon. And in terms of the quiddity sequence, that means that I am doing this operation. I have this number C1, C2, Cn minus 1, Cn. And somewhere between, I had a 1. But if I add 1, I change the neighboring values. Okay. If here I had Ci vertices, triangles, when I add this one, now I have Ci plus 1. And if here I had Ci minus 1, index I minus 1, now I have one more. Okay. So I can insert a 1 and change the neighbor anywhere, but for some reason I would always assume that I do it at the end. So we don't touch here. And between the vertex n minus 1 and between vertex n, I add a new one. So the quiddity will change like this. Okay. So this is an operation that is well defined on the set of triangulations. And I want to, so I will call this like augmentation, because if I had the length n here in the sequence, now I have length n plus 1. So if I had a triangulated n gon, I had now a triangulated n plus 1 gon. But we can also do the opposite, taking a quiddity sequence. It's not, maybe not obvious, but if you think about it or convince yourself with example, it's pretty clear that in a triangulated n gon or n plus 1 gon, I can always find in the quiddity sequence the number 1. There are always triangles at the exterior, at least 2 triangles like that. So I'm sure that there is a 1 somewhere. So I number the vertices so that the one is here just before the last. And if I have a triangulated n-gon, then I can remove, if at a vertex the quiddity value is 1, I can remove this vertex, and what I get is a triangulated of a polygon with less vertices. Okay, so this is the reduction operation. All right. Now for the proof of the theorem, I need to understand that this makes also sense on the frieze, on the set of frieze. So we want to show that these two operations are well defined on the set of frieze. Okay, so what does that mean? That means that if I take a frieze and if the first row give me this sequence, I can look at this new sequence, and this will define a new frieze with one more row. Or on the other way, if I take a frieze and if I find a 1 on the first row, I can remove this one and reduce by 1 the neighboring values. And what I will get is also something that defines a frieze with 1 row less. Right? So we will need a lemma. So I said that in terms of quiddity sequence, the existence of this one is pretty clear. Just look at the picture, convince yourself, or do an easy induction. For the frieze, we will also need this analogous statement. So let me call this a lemma. So the first row of a frieze always contains the 1. All right. So again, in terms of we somehow also need this lemma in terms of quiddities. We need to say that in a quiddity sequence there is always a 1, but I will assume that it's a easy lemma. But this one is less obvious. Okay, so if I want to understand these operations in terms of frieze, I kind of need a tool now that helps me to understand if given a sequence, is the sequence the first row of a frieze. So I need something that helps me to decide if I'm given a sequence, is it good for a frieze? And this tool is just an equation. So, and the equation will be given by a matrix equation. So let's call this equation of a frieze. It's a matrix equation, and I'm going to give in a moment. So introduce the following matrix. So I will use the letter N. Which is given by a product of 2x2 matrices of the following form. So here, the C's are just any, can take any values given n numbers, integer or whatever, complex. I can look at these 2x2 matrices obtained as a product like this. And it's not going to be too difficult to prove the following. So the first property or first proposition is that these matrices, this matrix N, they behave well with the operation that I just defined. So if you take this matrix, compute this matrix, it's going to be the same as the matrix of the augmented sequence. Okay. So here in this matrix, I have a product of n matrices. Here in this matrix, I have a product of n+1 matrices, but the result is the same. And this is very simple to prove because it's just some local property, because up to here, everything is the same. So I just need to check the product on the end. So the proof is just a local computation. We just need that if I compute with these 2 values, that's the same as that I compute with these 3 values, C+1 and D+1. Here I have a matrix obtained as a product of 2 matrices. I can compute this product of 2. Here it's a matrix defined as a product of 3 matrices. I can compute the product of these 3 and just compare, and you will see that it's the same. So this is proved. And this is very important for us, because now what I'm going to prove, so the second proposition is that C1, C2, Cn defines the first row of a frieze. So when I don't repeat, but I'm only considering frieze with positive integer entries. So here it's supposed to be positive integers. So these tuples of positive integers, they define a frieze, the first row of a frieze, if and only if. So the matrix N of C1, C2, Cn is minus identity. But it's not enough. We need to add a condition of, let's say, positivity. So we want that in the intermediate matrices C1, C2, Ci, I want to have positive entries in the second row of this matrix. So this matrix has positive entries in the second row. For all I equals 1 up to n-3. Okay, maybe before proving this, I just make a small comment. I will try to make it here in the corner. So, remark. So you may be familiar with this matrix, and in particular, if you had a look at the exercise sheet, there are some matrices that look the same, but not exactly. So just to make connection with the exercise sheet. So in the exercise, I think it's the number 5. We used.
Excuse me, Sophie.
Yes.
Sophie.
Yes.
Please be careful. Unfortunately, the very, very last part of your iPad, approximately 1 centimeter, is not reflected in Zoom. So if you could avoid writing in the very,
Yeah, no,
that's fine. Yeah, that's fine.
No, okay, sorry, I don't, okay.
Now it's fine. Now it's perfect. Now it's perfect. Yeah.
Thank you. By the way, are there any questions in the chat? Oh, no, okay. So I use a similar product of matrix, but the matrices were like this. So I will need to make connection with this exercise. And so what is the relationship between M and N? It's just that one is a transpose of the inverse. So it is just the same as the matrix N, but after transposition and inverse. Or if you prefer that, the matrix of the cofactors. Okay, so maybe I can also mention that this exercise will help us to prove the lemma. Remember, the lemma is here. Because so I say it here, so we will be done with this lemma. So the lemma of the previous slide is proved by exercise 5, question 3, and by proposition 2. Because in this exercise 5, what we showed is that if Ci is greater than 2 for all I, then what we have that in this matrix, we had entry, let's say Pn, Qn. So it's going to be the same in P, in N. But so what we proved is that in this exercise, so if this is like this, then Pn is positive. Okay, so the condition here, having the matrix N to be minus identity, it's the same condition than having M to be minus identity. So if the Ci's are all bigger than 2, we won't be able to find a minus identity because the value here always remains positive. So this is a way to prove that if we want, so if we know the proposition 2, if we have a frieze, this matrix is minus identity. But if the Ci's are all greater than 2, this is not possible. So we deduce the lemma that we have to have a 1 in the first row. Okay, so this is the proof for lemma 1, for the first lemma here. It's something that is shown in the exercise and a consequence of this proposition 2. Okay, so let us understand this. Where does this equation come from? So it comes from the recurrence relation in the frieze. Maybe I go back in the notes. Where was this? It was here. In the notes, I can find that we already seen that if I have a frieze along a diagonal, there is a recurrence relation of this form. Okay, so I'm going to reuse this. That's why I also use this key lemma, because this ingredient is very, very important for the proof I am doing now. So let's go back here. So recall recurrence relations. So we have a frieze, ones, and I call J and F, J2, F2, no, J2, J3, and so on up to JW. And the next diagonal will be called F2. No, sorry, I'm missing the indices. So this one was F2, and this one F3, FW, FW plus 1. Then I have the row ones. And remember, I said that we can, sometimes it's convenient to assume that we have zeros on the top. This does not break the rule of the frieze. And sometimes it's also even more convenient to also assume that we have a row of negative ones on the top. If you want the rule to be satisfied, there is no choice. For the row here, you have to have zeros. And for the row on the top, again, there is no choice. You have to have negative one. So I can assume, because sometimes it's more convenient, that here we have zeros and negative ones. Okay, and so what was proved earlier is that we have this relation between the gi equals ci gi minus 1 minus ji minus 2. And I can assume that the initial conditions for the g's are the following. I can assume that J0 is 1 and J negative 1 is 0. So I can compute the diagonal with this relation starting from J minus 1 equals 0 and J0 equals 1. And then the relation will give me all the entries on the diagonal. And I also have the same relation for the F for the next diagonal. For the next diagonal, I have the same recurrence relation, but with different initial condition, because this time F1 is here and F0 is this one. And so F negative 1 is minus 1. Okay, so F minus 1 is minus 1. And F0 is 0. Okay. So this recurrence relation, I can write them in the form of matrix. This means that the value fi minus 2, ji minus 2, fi minus 1, ji minus 1. I can apply some matrix in order to have to shift the indices. So to have fi minus 1, ji minus 1, fi, ji. So these 2 by 2 matrices, they are here in the frieze. And what I'm saying is that if I take a window here, I can compute the next window just by multiplying with some well-chosen matrix. And the well-chosen matrix is just the one that we had on the previous slide. It's just this one. Okay, this is the way to encode the recurrence relation in a matrix form. Okay, so what that means that if I start, so the initial conditions, sorry, the initial conditions are here. This is the 2 by 2 matrix of the initial condition. Then I multiply by one matrix, I will get this. The next matrix, I will get this one, and so on. So I can start with the initial condition here, apply first with C1, then with C2, and so on up to Ci. And I have the window corresponding of fi minus 1, fi, j minus 1, and ji. So what happens when I arrive at the end? When I arrive at the end, then I obtain this matrix, so that the opposite of this one. So for I, when I equals n, remember it's w plus 3. Okay, when I equals w, I'm here. When I equals w plus 1, I'm here. When I equals w plus 2, I'm here. And when I equals w plus 3, I'm here. So I obtain that starting from this, and then applying this product of matrices that I have recorded as the matrix capital N. No, sorry, there is no equal here. It's just multiply this matrix, the initial matrix, with this product of length n. Then you obtain 1, the matrix 1, 0, minus 1. So we obtain the conditions that we wanted, that this matrix n is minus identity. Okay, so let me say it again. If you start with a frieze, because there are recurrence relations in the frieze, you will find that this matrix has to be minus identity. But it's not sufficient. Why it's not sufficient? Because you can take several matrices with this property and concatenate, and you will not have only positive integer in the frieze. So it's not enough. So that's why I added this condition here. So let me refer to this condition as the positivity condition. If you start with numbers that satisfy only this, there is a good point, is that what you will get is a finite array. At some point, you will recover a row of ones, but between, maybe you have negative values. So you don't want that. So that's why we have to add this positivity condition. So the positivity condition is because in this matrix N, so this is the matrix N of C1, Ci. So the second row in this matrix is the same as the second row in this matrix. If you want N, is the same matrix, but with negative sign here. If you put negative sign here, it's the matrix N. So if you add the condition that the values in these rows are positive, that means that here you have positive numbers. And if you are sure, I mean, if you have positive numbers here, you are sure that everything is positive, because that's the rule of the frieze. When you compute, sorry, A, B, C, D, like this, D can be obtained without any subtraction. So by induction, by easy induction, you can prove that if all these numbers are, if a diagonal is positive, then the rest of the frieze is positive. Positivity propagates with the frieze rule. Or you can use more sophisticated arguments, and it was also a property that we saw last time. I say that if I choose a diagonal, all the entries can be expressed as Laurent polynomials with positive integer coefficients. So the positivity is pretty clear from different arguments. And so, okay, so actually what we have is, we have positivity up to n-2. We have even better, because if you apply again matrix. So I stopped here. I said that it's enough to check that all these values are positive, but actually the next one is also positive. But it's enough to check just up to n-3. Okay, so I mean, now we are completely done with the proof. I don't know if it's crystal clear for everybody, but what do we have? we wanted to show that this makes sense for the frieze, but it is pretty clear because now if we want a frieze, we want a sequence that satisfies minus identity plus positivity. Positivity. But this is completely equivalent to have this. So if this matrix is minus identity, this one is also minus identity because we say that these two matrices are already equal. So, and the positivity is you have to check condition up to n minus 3, but it's the same as here. That's going to be the same condition. But you actually know that it is true up to n minus 2. So this is I mean, the positivity, you have positivity up to n minus 2 here, which is what you need here to have positivity. So it's completely equivalent. So now the induction will work just straightforward. You assume that if you know that frieze with period n comes from quiddity sequences, when you take a frieze of period n plus 1, you look for the one, you remove it, you have a frieze of period n. So it comes from a quiddity, but the operation that you made tells you that this is necessarily a quiddity sequence because the operation is just equivalent to removing a triangle. So it works both in both directions. So with all of this, you are able just to rewrite nicely the induction to show this and to show that. So I don't want to write this in details, and I hope it's clear. If it's not, just tell me. Okay. So my plans was now to go back on different nice tricks that you can play with the frieze and triangulation. So let's go over new things. So more can be said or can be seen in triangulations and frieze business. So I have prepared, to make it faster, I have prepared a frieze, this one. So let's have a look at this frieze. So it has 1, 2, 3, 4, 5 rows. So it is associated with the octagon, a triangulation of an octagon. So let's draw octagon. 1, 2, 3, 4, 5, 6, 7, 8. Let's dot the vertices. And the game would be to, from the quiddity sequence, I mean, from the first row, to reconstruct the triangulation. So one should be able to do it because the theorem says that this is the quiddity sequence. So this octagon can be triangulated to have this quiddity sequence. But there is another trick that you can do. I mean, there is another way to construct the triangulation, and I'm going to explain this now. So the other way is to extract some a fundamental domain. As you know, the frieze has a glide symmetry, so I just need to focus on this green part. The rest of the frieze is just this part after flip and translation. And the trick I want to give you is that to construct the triangulation, we only need to understand where the ones are located in this domain. So cut the frieze anywhere you want along a fundamental domain, and look at the ones. Now you have to imagine that you are on a grid. So let's call the entries of the frieze E11, E22, E33 in the first row. So I make a label on the entries. I also use this in an exercise, so I don't know if you had time to have a look. So these are double indices for the entry in the frieze, and the recipe I will not prove. It's proved in this Conway-Coxeter paper. Is that if you find a one, if one of these value equals 1, then in the corresponding triangulations, you have that the vertex I-1 is linked to vertex J+1. Okay, so let's do it. So I don't know, suppose that this is your vertex 1, vertex 2, vertex 3, vertex 4, vertex 5, vertex 6, vertex 7, vertex 8. It's the same as vertex 0. So what do I read in this? So this entry is this one. So what do I read? I read that E11 equals 1. So that means that vertex 0 is linked to vertex 2. Then I read that here this entry is 1. So that means that vector 0 is also linked to vertex 3. And vertex 0 is also linked to vertex 4 and to vertex 5. So I draw here. And then there is a remaining one, which is located further here. So which one is this? It's 1, 2, 3, 4, 5, 6. So that's E66. So that means that the vertex 5 is joined with vertex 7. Okay, and check. Look at the quiddity sequence. It is 1. It is in red. This is 1, 2, 2, 2, 3, 1, 2, and 5. Okay, and this is what you read here: 1, 2, 2, 2, 3, 1, 2, 5. So that's the triangulation that we were looking for. Okay, but it's I will not explain why this works, but it's kind of nice to know. And finally, I said I also want to go back to this question of continued fractions. So let me again, I'm going to reuse this picture. Okay, so this, and yeah, I'm gonna erase also the numbers here. So I clean a little bit. So I'm gonna reuse the picture, but with different operations. So yes. In this example, as you can see, that's in this triangulation, I have two exterior triangles. I can join them. So now in terms of quiddity, exterior triangle means vertex where the quiddity is 1. So that's equivalent. We have only two vertices where the quiddity is 1. If I join these two vertices, I cross all the other triangles of the triangulation. And if you remember from the previous, from the first lecture, we say that this encodes the conversion of continued fraction. So this triangulation is associated with a rational number. Which one? Which one? So yes, so let me write. So I need to understand the sequence of triangles. This triangle has the base under the pink line. These triangles have bases above, and this one has the base under, and this one I assume it's above. I always assume that the first one has the base under, and the last has the base above. Okay, so I have remember, we can count this sequence of triangles. So I said the first one is base below, then I have 3 triangles with the base above, then I have 1 triangle with the base below, and 1 more triangle with the base above. If I can consider that this triangle has the base under, and it doesn't matter because these two fractions are the same anyway. And the picture gives me the conversion for the continued fraction with negative sign. I just need to count. The recipe was to count here. So I had 2, 2, 2, and 3. So the recipe tells you that these numbers, sorry, 2, 2, 2, 3 form the sequence for the expansion with negative sign. But so what is the rationale behind this? Okay, let's try to, so we can compute the fraction. Okay, it's just elementary arithmetic, but there is another way to understand this rationale. So I'm gonna tell you now. So the way is to look at, to play a game, which will be called the Farey sum game. And the game is the following. You assign to the vertices in the triangulated polygon rational numbers. So we will start with the rational number 0/1 here. And on the top, I will assign, maybe I erase liquidity. I'll assign the number, it's not really rational number, it's the infinity 1/0. And now the game is that to complete the picture so that I have, when I have assigned 2 rationals at the vertices of a triangle, the third vertex is assigned with the Farey sum of the 2 rationals. The Farey sum is just to make the sum of the numerators and the sum of the denominators. So we play the game all around the picture. So let's do it. So I have a triangle here. 2 vertices are assigned with a rational, so I can compute, assign to the third. So here it's just sum of the numerators and sum of denominators. So now I have this triangle in which I have 2 already assigned numbers, so I can deduce this one, and then I will have 2 in this triangle, I will deduce this one, and then I will deduce this one, and so on. So let's do it. So this one, sum of the numerators, and sum, and this. And now what can I do? I cannot go along here. I need to go under and look at this triangle. And so this triangle will just sign 5/4, and the next one will be 9/7. And so now what I claim is that this last assigned number, 9/7, is exactly the value here of the in this row. Okay, so really the triangulated polygons carry at the same time the rational and the decomposition as continued fractions. And what about the frieze? Can I see this 9/7 in the frieze? Yes, I can. So there is a glide, so I can see in 2 different ways. Maybe I see 7/9, but I just need to turn my head and pretend that I see 9/7, or maybe just choose the glide, because with the glide now we also have 9/7 here. That's the same. So the piece that is here start with 2, 2, 2, 3, 2, 2, 2, 3, which is the expansion of 9/7. And the frieze rule allows me to compute this rational. So it's a kind of a frieze. It's a kind of equivalent way to compute continued fractions with negative sign. And if you know continued fractions with negative signs, you will find that they set the numerators and the denominators from sequences with the same recurrence relation. So sorry, I see chat.
Yes, there have been quite a lot of discussions, Nelly, sorry, Sophie, but it looks like many students now picking this up. So maybe I'm not sure if any students still have the questions. Maybe if students still have questions, maybe they can switch on their microphone and say if there are any remaining questions.
Yes, I went too fast when I was counting the. Sorry. Okay. So for the last question, no, it does matter which exterior triangle you start. I mean, I always assume the orientation clockwise. So if you turn the picture, then we have this sequence in the other way round, and we have another quiddity sequence. We have the quiddity here that is 2 and 5. So I don't know if I can do this. Let's try. To answer the last question. So I think I can turn everything. And so now if I turn everything, so the quiddity sequence here is 2, 5. And this blue sequence is to count the triangles under and above the pink line. And so it changes this, it is, now it's 1, 1, 3, 1. So actually what we can deduce is that we can deduce that 1, 1, when you reverse the sequence in this fraction, then what you will get is this. But anyway, I see that there's only 5 minutes. Does this answer the? Okay. And let's go back on the Farey sum business. So I only have 5 minutes. I'll try to go fast. I prepared a picture which extends this Farey connections. On Monday, in the talk of Caroline series, the colloquium talk, she talked about Farey tree, and it's just the dual version of the Farey tree. So in the Farey graph, what is a Farey graph? So Farey graph, so for the vertices, we will have the rational numbers, including infinity. And for the edges, we will draw an edge between two rational numbers. So I always assume that they are written as irreducible fraction. And you put an edge, usually as a half circle, whenever the quantity pq prime minus p prime q is plus or minus 1. So in the Farey tree, the rationals are labels for the regions between the tree, between the branches of the tree, and the regions are adjacent if we have this property. So here it's really a dual version. Instead of the regions become points, the rational, and you draw an edge whenever you have this thing that is satisfied. Okay. So the best way to draw the graph is to draw it in the plane. You put the rational on the horizontal line and you draw the edges like half circle. And what will happen is that, so it's an infinite graph. So you can, I'm trying to extend the graph. I don't know if you can always continue the graph. And what you have locally is that you have a picture that looks like this. So it's a tessellation of the half plane with this shape. And the vertices are all of this following form. So here the rational numbers are put in increasing order. There is a question in the chat. So, but I don't use a real scale because here you have 1 and 2, so there is a difference of 1. There is 2 and 3, so the length seems to get shorter and shorter. So the unit is not clear, but so put the rational in increasing order in this line and finish the line with the infinity point, and then draw this, and you will have this picture, a kind of fractal picture. And what is interesting is that there is no crossing edges. It's not possible that somewhere there is a rational that is linked to another rational like that. There is no crossing. So you really have some partition of the plane. And this is a natural picture to consider continued fraction. Why? Because what you can do, okay, if you are, so pick up a rational. If you are interested in the continued fractions of this rational, what you can do is just draw a vertical line. And this will extract from the picture finitely many triangles. So this is called a triangle, okay, now when I say triangle, I mean this shape. So this line crosses finitely many shapes. So just look at what you cross. I did it here. I start with 7/5. I draw this line. So I removed all the non-crossed triangles. So I have a finite picture. And the finite picture is just, it comes like a triangulated polygons. So in this picture, you play the same game, but now instead of talking about below or above the line, I talk at the left or at the right. So I go this way. and I count how many triangles are at the right or at the left. So I have a sequence. So the ones that have the base at the left, they are pink in the picture, and the triangles that I consider with the base at the right, they are purple triangle. Okay, so when I read this sequence, I have one pink, two purple, one pink, one purple. And this tells me that this is the expansion of the rational 705. This is actually something that can be found in Caroline series paper in 1985. But now with this Conway-Coxeter theory, I know also that if I count the quiddity, if I count how many triangles I have here, it's gonna give me also the sequence for the negative expansion. So it's 2, 2, and 3. So in the same picture, in the Farey graph, in the same picture, I can read the expansion with the regular continued fraction, and I can read the negative expansion. I can also find the frieze because triangulated polygons are frieze. So I did it here actually. So this triangulation, if I draw it in the Euclidean way, I will have this. And the frieze is already here because all this rational can be viewed as diagonals in the frieze. So I take here 1, 2, 3, 7, 4, 1. I put them in a diagonal. I compute the frieze. And this is exactly the frieze associated with this triangulation. So I'm sorry because I feel that I am over time, so I don't want to tell too much. So I don't know. I just wanted to point out that in the same picture I have the continued fractions and the frieze and the triangulation at once. So I see that there are questions again.
Sophie, there is a principal possibility because you have the following lecture.
Yes,
so
yes.
Start with the questions.
So yes, so I'm gonna record the question.
Because the questions will not disappear since we are still in the same meeting. The questions will remain there.
Okay, so I just the dotted line connected. Yeah. Okay, so there was a question on this dotted line. I don't imagine that it's connected to any points. It's just a way to extract a finite picture from the previous one that was infinite and remove the non-essential triangles. But it's not a geodesic, a real geodesic as you wanted to have. Okay, so sorry, so yeah, I mean that's the line that is connected somehow these two. Yeah, I mean I should have maybe drew like this, but so this dotted line, sorry, would be more like this one, but going then no, sorry, like the infinity. Okay, no, so I don't know if it makes sense. This one is 0, and this one is 7/5. So I don't know if this answers the question. Okay, so sorry, and we need to get some rest before the start of the next lecture. So thank you very much.